Hi, in these next two videos, I will be going over how to enter input data and analyze results for the add-on module RF Concrete members. I will be using the ACI 31814 code for designing these members. In part 2, I will go over the results and explain how to analyze them efficiently. So let's begin. Right now in the graphical area, I will be using a simple concrete moment frame, and this moment frame has a uniform dead load of 1.8 kip per feet and a uniform dead live load of 3.6 kip per feet. You can also see I have LRFD load combination. So to start off, to access the concrete member module, we can either go to the list of modules in the project navigator over here on the left side, or we can go up to the toolbar and go under add-on modules, where the modules are categorized better and based on what material you would like to design. So we'll go up here to design concrete, and then we can come down here to RF concrete members. So you can see when I open the add-on module, it is pretty much just a dialog box, and all of the loads, load combinations, materials, cross-sections are imported from RFEM automatically. The only thing that we really need to define here is a little more information for reinforcement that is specific to the ACI 31814 standard. The first thing when opening the module is you want to pick what standard you're designing per. You can see we have both the ACI and the CSA along with Eurocode and some others. For this example, we're going to be designing per the ACI, and for our strength limit state design, I will pick LRFD. You can see that this LRFD has already been moved over to the right. And then for serviceability limit state, I would choose my ASD load combination. We can choose all of them at the same time and move them over to selected for design. And then down at the bottom under serviceability limit state, I would like to point out that this is where we have the option to activate RF concrete nonlinear. I won't be activating that for this example, but just keep in mind that this option is here if you have the module extension to utilize the crack cross-section properties within the analysis. Now, we can just simply move down the list here on the left-hand side from top to bottom. The next section to move on to is materials. Here you can see we have 4,000 psi concrete, which was imported from RFEM, and our reinforcement material is set to grade 60. You can see the material properties are also listed below. The next thing we can move on to is cross-sections. Cross-sections is similar to the materials section, with the fact that they are all imported from RFEM into the module. If I move the window down, you can see that when I click on a cross-section, it is highlighted in the RFEM model as well. Also, I'd like to mention if you have any ribs that are designed within your model, this tab will appear on the left-hand side, and then you can see where the rib starts and ends, as well as what surface it is integrated with, along with the effective widths. The next tab for us is the supports tab. This is used by first selecting the nodes at the end of our beam. We can do this graphically in RFEM, and the reason for this is to define whether the column is underneath the beam or if the beam is framing into the face of the column. You can see in the picture on the right what each of these options change. We'll just assume the beam is framing into the side of the column. You can also see when I change these support properties how the picture on the right hand side changes based on what I've selected. Also, what this tab allows us to do is to reduce the shear forces in the support area according to section 9432. This says we can consider the beam a D distance away from the face of the column, and D is the depth of the beam. So the shear forces at that location will be used for the shear design, so the ACI allows us to reduce those forces so we don't have to, so we don't over design that shear reinforcement. And the last tab is our reinforcement tab, which is the majority of the work we have to do before we can hit calculate. So the first thing to do is to create a reinforcement group. The description of the first reinforcement group will be for our columns. Now I don't want this to apply to all of my members, so I can go over here and unselect all, and now I can select my columns graphically. Now for the longitudinal reinforcement, I'm only going to select the possible rebar sizes that I want the program to take into consideration for design. For example, let's say I only want my columns to have either number 7s or 8s. I can select those. Up here we can select the maximum number of layers. Right now the default is 1, but maybe you have a deep beam member and need to set more layers. You can do so with this drop down over here. The anchorage type is our development length, and you can see the options we have, such as a bend or hook. The program can give you dimensions for that based on the ACI standard, along with our applied internal forces. For now, we're going to keep this as no anchorage type. Next, the curtailment type allows us to specify different areas within the member length that might need additional longitudinal reinforcement. For example, our beam member could have significantly more bending at the middle compared to the ends. So what you can do is set different curtailment types. So longitudinal reinforcement can be set for different zones. For this example, I will be using no curtailment, which keeps the long reinforcement uniform throughout the beam. The next tab is our ties and stirrups. For the bar size, we have the same concept. For this example, I will choose number 4s, which is already selected. The default option is to use uniform spacing throughout, and that is what I'm going to keep. The program can also take into consideration max stirrup spacing based on the ACI standard. It will either design or flag us if we exceed the maximum spacing. Following that, we have our reinforcement layout, and the first thing to check is the concrete cover. The ACI standard refers to table 26131 for concrete designation. In this table, it shows you if you're using number 5s or smaller, and this will tell you to use a 1.5 inch for the cover, which should be adequate. If the program comes up with larger bars, I would want to come back and adjust this. Since we are designing our columns here, we want the reinforcement layout to be designed for a column, and you can see in the picture on the right over here, this is more for a beam. So we want a design that focuses more on biaxial bending. So using this drop-down box over here, we can choose uniformly surrounding. And now you can see over here on the picture that it's changed, and now the reinforcement is more effective for a column member. The relevant internal forces that we'll be designing for our column include axial, shear, and moment, along with torsional forces. Keep in mind, if you don't want to design your columns for torsion, for example, you can just uncheck this box. For the minimum reinforcement tab, you can just keep in mind that these checkboxes should be efficient. This is going to refer back to the ACI standard and use this to provide minimum longitudinal / shear reinforcement based on the ACI. We also have the option to set a minimum reinforcement manually if you would like to. Next, the ACI tab contains just a little bit more information on the ACI standard alone. For example, the max percentage of reinforcement is set to 8%. This is from the ACI section 10.6.11. This just means we should have no more than 8% steel to concrete ratio. Same thing for shear and torsion reinforcement. These are just settings according to the ACI chapter 22. Then we also have our reduction factors, which come from 21.2.1. These are all set to default from the ACI standard. You can adjust these if you'd like. The last tab is our serviceability tab. I just want to point out that the only reason we have this tab is because back under the general data tab, I moved my ASD load combinations over to be designed. If we did not do this, then we would not see that serviceability tab. For example, I'm designing for serviceability according to ASD load combinations. So there are two considerations for designing serviceability. We have cracking and deflection. With cracking, the first thing we want to specify is the crack width limit. We can limit the first option, which is to utilize the drop-down box that has a few default options. These just come from the ACI committee, who has done some research and put together some recommendations based on where your structure is located in a used dry environment. For this example, I would just assume cracking is not much of a concern. You can also set this to user-defined, so you just have to manually type them in. Below we have two different checkboxes. One is design without crack width calculation according to 24.3.2, which if we leave this checked, we are just making sure we are adhering to the ACI's rule on reinforcement spacing to prevent cracking. The next checkbox that says design with direct crack width calculation just applies the Gergely-Lutz equation, which is a much more theoretical equation for calculating crack widths and compares to the limiting value above. For deflection analysis, you will notice when I check this box, I will then gain an additional table for deflection data over here on the left-hand side. The option to activate long-term deflection according to 24.241 is here, and I can just input the duration of the loading in months. Under the deflection tab, there isn't much to do here. The program already knows to add both the columns to this table. The reference length is set to the distance between the supports. If we had a pre-camber, we could put that in right here. Then in the next column, we have our limiting values in the dropdown. These are values directly from the ACI, or you can type in your own user-defined values as well. The next column, you can see that we can now not exceed a value of 0.48 inches. The program will compare the demand deflection to our limiting deflection and give us a design check ratio for serviceability. So that was the majority of everything that needs to be entered into the module before you can run your calculations. Also, don't forget that was only for our columns though. I would also like to design the beam as well so what we can do is easily just make a copy of the current reinforcement group, and now I can just rename this reinforcement group beam, and now I just go over here and I can deselect these members, and now I can select the beam graphically. So now most of these tabs remain unchanged, and we can turn on zone-related spacing down here, which will change the spacing for ties where there is an increase in shear compared to the other parts of the beam. Here you can select how many different zones you would like. I'll keep it as 3 for now. The cover is correct, but we will have to change the reinforcement. We can change this reinforcement layout to optimize distribution. So now you can see we are getting it for the top and bottom. So for the rest of these tabs, we can just leave them the same. Now you can see under the deflection data tab, for serviceability, our beam was added, and the allowable deflection for that is 0.96 inches. So now we have finally entered all of the data we need to run our calculation. This is the end of video 10 part 1, but I hope you continue to watch part 2 where I'll go over the result and how to view those. If you have any questions, please leave a comment below or email us at our tech support email in the description below. We also have a lot of helpful FAQs and knowledge-based articles on our website at dlubal.com.